Thousands of kilometers beneath Africa, hidden far below the surface, is something scientists still struggle to fully explain. We cannot see it directly, we cannot drill down to it, but earthquakes have given scientists a way to detect what lies deep inside our planet, and what they found is enormous. To understand what is hidden beneath Africa, scientists have to listen to the Earth itself. Every earthquake sends vibrations through our planet, traveling far below the surface. As these waves move through different layers of rock, they can speed up, slow down, or change direction. And those tiny changes give scientists clues about what lies deep beneath us. Researchers can compare signals from earthquakes recorded around the world and use those differences to build an indirect picture of Earth's interior. But there is a limit to what these measurements can tell us.
We can't go down there and take a sample. We have to learn from the signals that reach the surface.
So scientists compare thousands of observations, searching for patterns that should not be there. And beneath Africa, those patterns revealed something enormous.
What makes this interesting is that the signal is telling us something about a part of Earth we can never directly visit.
When scientists combine seismic measurements from around the world, they can create something remarkably close to a map of Earth's interior. These maps are called seismic tomographic models. And when researchers looked deep beneath Africa, the data revealed a region where seismic waves travel unusually slowly. It was not a small pocket of rock. It stretches for thousands of kilometers through the deep mantle, close to the boundary between the mantle and Earth's outer core. But calling it a blob can be misleading.
What we're looking at is a seismic anomaly, a region where waves behave differently from the surrounding mantle.
Scientists can map its shape, but its actual composition is much harder to determine. And that is where the mystery becomes much deeper.
The fascinating part is that we can map something this enormous without ever physically reaching it.
But mapping the anomaly creates another question. Where did something this enormous come from? Scientists have proposed several possibilities, and none can yet explain every detail with certainty. One possibility is that ancient material sank deep into Earth's mantle and survived for billions of years. Another idea is that massive amounts of dense material accumulated there over immense periods of time. But there is another possibility. The structure may contain remnants of material that have been different from the surrounding mantle for an extraordinary length of time.
The evidence suggests this material has behaved differently from the surrounding mantle for a very long time.
The problem is that seismic waves can reveal differences, but they cannot simply tell us what the material is made of. And that uncertainty is what makes the African anomaly so difficult to explain.
What we know is that this is not a simple story. The deeper we investigate, the more complicated the evidence becomes.
The strongest clues come from the way seismic waves move through the deep Earth. Different materials can change those waves in different ways. And beneath Africa, researchers found unusually slow wave speeds across a region far larger than anything near the surface. That difference became one of the anomaly's most important signatures. But a slow seismic signal does not automatically tell scientists what the material is.
The velocity tells us that something is different. It doesn't tell us exactly what that something is.
Researchers, therefore, compare several kinds of seismic measurements to test whether the pattern remains consistent.
And the more measurements they compare, the harder it becomes to dismiss the anomaly as a simple mistake.
The important thing is that we're not relying on one earthquake or one measurement. We're looking for a pattern that survives different ways of looking at the Earth.
The deeper scientists investigated, the older the story seemed to become. Some evidence suggests the material inside these enormous regions may have survived for billions of years. That would mean it could have endured changes that completely transformed Earth's surface. Continents moved, oceans opened and closed, while deep below, something remained. But surviving for billions of years would require an unusual kind of stability deep inside the planet.
If this material is truly ancient, it may preserve a record of Earth's earliest history.
Scientists therefore look for chemical and physical clues that could reveal whether its roots reach deep into Earth's past. And one clue in particular has made the region even more intriguing.
We are looking at evidence that could potentially tell us something about a much younger Earth.
One of the biggest clues comes from the chemistry of volcanic rocks found at Earth's surface. Some of these rocks carry unusual chemical signatures linked to material from deep inside the planet. Those signatures can survive when tiny amounts of deep material rise toward the surface. And for scientists, they offer a rare window into regions we can never physically reach.
These chemical signatures are important because they can preserve evidence from much deeper inside Earth.
But scientists still have to connect those surface clues to structures buried thousands of kilometers below. That connection is difficult because the mantle is constantly moving and changing. Yet some evidence points toward a history far older than the world we see above it.
What makes these clues fascinating is that we are trying to reconstruct a history that began long before humans were here to observe it.
Scientists cannot drill anywhere near the mantle, so they use something Earth produces naturally: earthquakes. Every major earthquake sends seismic waves traveling through the planet in different directions. When those waves encounter different materials, their speed and direction can change. By measuring those changes across thousands of recordings, scientists can reconstruct what lies deep below.
The result is not a photograph of the deep Earth, but a model built from countless pieces of evidence. And when independent measurements repeatedly produce the same broad structure, confidence in the model grows.
We don't see the structure directly. We see its effect on seismic waves.
That distinction matters because the evidence is powerful, but the deeper questions remain.
The remarkable thing is that earthquakes become our instruments. Every wave gives us another piece of information about a world we cannot reach.
After decades of earthquakes, measurements, and computer models, scientists have built an extraordinary picture of Earth's deep interior. But the African anomaly remains a reminder that our planet still holds enormous structures hidden beyond human reach. Its exact origin and composition are still debated, and new evidence could change the picture again. What we know is that something vast exists deep beneath the continent, revealed not by sight, but by the movement of waves. And perhaps that is what makes this discovery so fascinating. Earth can reveal its secrets without ever showing them to us directly.
There is still so much about our planet that we have never been able to see.
The anomaly is not a finished mystery, but a doorway into questions about how our planet formed, changed, and survived. And thousands of kilometers beneath Africa, that story is still being written.
Sometimes the most extraordinary discoveries are the ones that remind us how little of our own planet we can actually see.